call Rosa from University of Cambridge, and thank you very much.
Thank you everyone for being here, and thank you the organizers for inviting me to give this talk. So I'm going to talk about specifically nonparametric regression today. So we had a little bit of that this morning, but I'll go in another direction, kind of. So basically what I'm going to try to introduce first is something called the testing condition, which is a central kind of tool or problem depending on how you look at it in Bayesian nonparametric theory. So first, let's forget anything about being Bayesian. Like, let's say you want to solve a high-dimensional nonparametric estimation problem, and so what you want to estimate is an f-naught given some observations based on it, where f-naught is a parameter, so density function, regression function, anything. And so you produce an f-hat, okay, to estimate f-naught, and then you choose a measure of discrepancy d, and what you would like to do is to ensure some condition, some bound of this form, okay, so it can be an expectation, can be probability, I don't know, but yeah, you want to ensure that the distance between f-hat and f-naught is small, depending on how we choose this measure of distance, okay? And what you want typically is to guarantee that your epsilon n is some kind of optimal in a way, and arguably speaking, the most commonly chosen framework for this is the minimax theory, okay? And that's the kind of things we're trying to aim for, especially in this talk. So minimax theory for high-dimensional or non-parametric estimation. And in the Bayesian setting, you don't really have an f-hat, okay? You can produce an f-hat based on a Bayesian posterior distribution, but the whole point of Bayesian inference is to have a whole spread of posterior distribution to base your inference from, even though we won't be talking about uncertainty quantification here, but that's kind of the idea you have to keep in mind. And so you have to replace this kind of first line of frequentist upper bound into something that's more tailor-made to the Bayesian framework. And I'd say the most commonly found kind of alternative to this formulation to the Bayesian framework is something of this kind, okay? So what you want to say is that based on some rate epsilon n and your posterior distribution pi given the data, the posterior probability of the complement of an epsilon ball around f-naught goes to 0 in probability under the probability of the probability distribution of the data. So what we're doing here is we have a Bayesian tool, okay, so the posterior distribution, which is constructed from a prior and some observed data. If you're only being Bayesian, then the data is fixed and you're playing with your posterior distribution. But what we are going to do is to analyze the behavior of this posterior distribution if you assume that the data is not fixed but generated itself in a frequentist way as above. Okay? So that's why we formulate this kind of contraction rate for the Bayesian posterior distribution as the fact that this posterior probability of the complement of the epsilon ball is going to 0 according to the data generating distribution, which is the frequentist object. Okay? Just to clarify the framework. Okay? So it's a really heavy third slide in a way, but I'm not going to try to explain it all at all because that's not really the purpose of this talk. But basically, there is some kind of gold standard approach in order to show that a given rate epsilon satisfies this kind of condition, which is usually referred to like the testing approach or prior mass and testing approach. And it relies on a set of assumptions, okay, that look really, really complicated, but actually it's not that hard once you're used to the framework. But anyway, you have a bunch of things to satisfy. So basically, you have the existence of a set of parameters, so a set of density if you're doing some density estimation problem that has sufficiently large prior probability, prior mass. It must have a control complexity measured in terms of metric entropy. And the prior mass of some well-chosen neighborhood around the true distribution of the data must not be too small, okay? And the neighborhood of the distribution of the data is measured in terms of Kullback-Leibler type divergences. Those are the first three assumptions, but the last one is the one that we're going to focus on right now. Is the kind of testing condition, which is the only thing. If you have to understand one thing about this slide, is that basically you can't choose D as you want, and that's the whole problem. Is that you're really constrained. Your hands are tied in what you can do or not do with this kind of approach. And so that's the whole problem, really, in a lot of cases, is to show that. Well, you can choose a distance that satisfies this kind of testing condition that I'm going to introduce just in the slide after. But if you have those kind of four conditions that are satisfied, then basically you can guarantee that this kind of rate epsilon max, epsilon n bar is a rate as I've introduced us before, so a contraction. And the testing condition here is basically you have to show that for the distance d that you're choosing, you can theoretically construct tests that satisfy this kind of bounds on type 1 and type 2 errors. So it's a kind of structural assumption on the distance d based on the likelihood model in a way. So it's not easy. It's really not necessarily something trivial to show that you have a natural measure of distance. So I don't know, if you're doing density estimation, you're taking the L2 distance, then it's definitely not really easy to see, unless your densities are, for instance, bounded or something. But in general, it's quite a pain in a way. So as I said, so let's look at some examples. So let's say you're trying to do density estimation. So your parameter is in dimensional density. Okay, you're trying to estimate using mixture models, exponential family, anything. Then what you can always take is the Hellinger distance or the total variation distance. So those two can be seen to satisfy the testing condition. And typically, if you choose your prior well in a reasonable way, at least for a large class of kind of popular priors, you can show that the Bayesian posterior distribution will indeed lead to like minimax optimal contraction rate for those kind of metrics. But as I said, we're not going to focus on that. We're going to focus on regression. Okay. So you observe yi equal f naught of x. There's a typo. It's xi. Okay, not xn. F naught of xi plus epsilon I. So here we're focusing on normal errors, but you could take other kind of errors under some assumptions, of course, but it's not really crucial that we're having Gaussian errors here. Then basically, what you can take as metrics that satisfy the testing assumption in this kind of problems is the root mean squared error here. Okay, so we're taking the L2 norm, but with respect to the empirical distribution of the covariates xi. Okay, so that can be seen to satisfy the testing assumption using some kind of likelihood ratio tests, okay? Or you can take, basically for the same reason as the first point, you can take the Hellinger distance between the distribution of the observed data, okay? If assuming that your design is itself random, okay? So we're gonna focus on this case where the design is actually random, okay? So xi is IID, according to the distribution P naught. And if you look at the Hellinger distance between the data generating distribution defined by f and f naught, you're just ending up on this kind of discrepancy. Okay, so basically this one here, it almost looks like the L2 distance between f and f naught, okay, measured according to the distribution P naught, only that is kind of capped for the high values. Okay, if f minus f naught takes a super large value, then the exponential goes to 0, and then the whole error goes to 1, basically. So you're not seeing really the high discrepancies. But around 0, then it's comparable to a quadratic, and then you have something that's more or less like an L2 norm. Okay. For the first one, we're truly having an L2 norm. Okay. It's the L2 norm between f and f naught measured in terms of the empirical distribution of the x size, but it's really just measured at the x size. Okay, it's not measured on the whole space on which f and f naught are living. So it could be that okay, you've managed this same metric satisfies the testing condition, so I can apply my whole machinery of prior mass testing approach. I show that basically the Bayesian procedure converges at a minimax rate with respect to this semi-metric, but there's no guarantee that it's going to behave well outside of the design points. So it's a bit, yeah, it's not really satisfying condition to be in, basically. So what we're going to do is to try to basically turn this into the true integrated L2 norm weighted by P naught, which will look more like this, but without this kind of exponential link, the true L2 norm. So there are already ways to do that exist in the literature, but they always assume some kind of extra assumptions on F naught, which is kind of annoying, and that's the thing we're trying to get rid of here. So as I said, we're going to try to aim for the L2 of P naught metric, okay, instead of those two semi-metrics that were not really satisfying. And yeah, because as I said, basically there are ways to basically get this kind of norm here based on. So typically, what's done is you first show a result under the empirical L2 norm, and then you try to extend it by some kind of concentration argument to the L2 norm. And that's where the problems arise. And yeah, you have case-by-case arguments. So the two ways that I know of that exists up to now that still lead to minimax optimal estimation rates under the L2 norm for kind of generic kind of Bayesian inference kind of procedures. And I know two of them. Those are the only ones I know. The first one is to basically clip the posterior. So instead of looking at the posterior distribution of F, you're looking at the posterior distribution of F, but capped between two values minus M and M for some fixed M. And if you know that your true F naught is itself taking values in minus MM, then basically you're going to be doing good work and things are going to work. Because you can use empirical process theory to relate empirical L2 norm and true L2 norm. But you require boundedness, and if you don't know an a priori bound on the F0, you're a bit doomed. You can't really do that. Okay. Although in some cases you could argue that you know an a priori bound, so it depends what you're doing actually. But in all generality you cannot. Okay. And otherwise, another approach is to directly use the fact that the empirical L2 norm is, I mean, the squared is obviously an empirical mean, okay, and so you can apply a concentration inequality to basically show that this is close to its population value, which is the L2 of P naught norm, okay. But the problem is that basically, if you're doing that, then you're in a minimax kind of framework, so basically your rate will depend on the regularity of your underlying parameter F0. And the problem is that you won't be able to do this kind of Bernstein inequality argument unless the regularity of F0 is larger than some threshold, which depends on the dimension of the input space. Okay, so the dimension in which the xi's are living. So, namely, it needs to be smoother than d/2 if this is the dimension of the input space. And it wasn't really clear if there was a true limitation, like if basically things were not working below d/2, or if we could find alternative arguments. Actually, for a large class of priors, as I'm going to show here, you can actually get for free basically L2 contraction rate below the d/2 threshold, which is the whole point of this organization. And we're still going to be relying on Bernstein's inequality, but instead of applying it to this empirical sum here directly, we're going to use the matrix Bernstein inequality, basically, instead of the scalar one, applied to the empirical inner product matrices of some well-chosen functions, basically. So here we are investigating priors that are based on random series. Okay, so you have a bunch of different priors that you could take to estimate a regression function. Obviously, the one that comes to mind almost directly is the one of GPs. Okay, you take a Gaussian process, then you look at the posterior GP, and then you can base your inference on that. And there are different ways to define GP. So you could take, the kernel approach, where you just define a center GP just by defining its covariance kernel. okay, so matterns, co-exponential, I don't know. Or you can also say, I'm going to look at a series like that, so f equals the sum of Cj uj, where C is a big vector, possibly infinite dimensional, that has some kind of Gaussian law, okay, and uj's are basis functions. It turns out that for the theory here, we don't really need it to be a GP, so you could take any kind of law on the, I mean, not any, obviously we're going to have assumptions, but it doesn't really, the fact that you're looking at Gaussian processes is not really central to the idea. And what's more important is are the conditions satisfied of the basis uj itself. So let's say that, so basically your xi's are living in some space capital X that's measured, so it has a reference measure mu, okay? uj is an orthonormal basis of L2. Actually, it's not really central. You could take a frame, if you know what that is. Basically, you don't really need to have strict orthogonality. You just need to be compatible with the L2 structure in a way. What we're also asking is that the density of P0 with respect to mu exists, okay, and is upper and lower bounded. Okay, it's not that restrictive. And most crucially, what we need is some kind of bound here. So you're looking at the first capital J basis functions, okay, U1 up to U capital J. You sum the squared of the uj, so sum of uj squared of x, okay, for all x, and you want to ensure that the supremum over x of this quantity is less than c squared capital J. So your constant times capital J, so the number of basis functions that you have. So it looks like a weird kind of assumption, but actually it's kind of ubiquitous in any kind of priors, basis functions that are used in the field priors in BNP, they're kind of always kind of satisfying these kind of things. So for instance, if you're taking a random trigonometric series, okay, Fourier series, then obviously this is satisfied because the UJs are uniformly bounded. So you're going to have this kind of bound that's satisfied. If you're taking, instead of Fourier series, not necessarily the most useful ones in terms of analysis, typically wavelet series are more well behaved because you can relate them to base of spaces, those kind of things. So instead of UJ, you have a wavelet basis PJK, okay, where J is the resolution level and K is the kind of spatial index. Then if you look at the sum of CJK squared of x, okay, sum over J less than, let's say, capital J and then K in I small j. Okay, it's kind of the analog of this sum here. Okay. Then by kind of standard localization arguments for wavelets, actually, this is less than a constant times 2. So let's say you have a basis on 0, 1 to the power d. 2 to the jd over 2 times the maximum over k of psi j k of x. And in the same way, this is bounded by 2 to the jd over 2, just by construction of wavelets. They always satisfy this kind of bounds, perhaps up to a constant, of course. And so you're left with, up to a constant, the sum of 2 to the jd for j less than capital J, which is exactly the number of basis functions if you stop the decomposition level up to capital J. So up to a change in what capital J means between those kind of things, you have the same kind of property that's satisfied. Okay. And then another kind of important basis functions that you could take are the ones that are the eigenfunctions of Laplace-Beltrami operators on compact manifolds or Laplacian on regular domains over D. And by alternative arguments, which are not really that do not really look like those kind of trivial manipulations I've done here, you can show that indeed you have this last bound that's satisfied. Okay. But I'm not really going to do into the proof of that, but just trust me on this, basically. And those already cover quite an extensive amount of priors that are used. I mean, as I said, it's not really easy to think of something outside of those kind of examples. But anyway, so that is all to say that this is not super restrictive thing to assume on the basis. And what's happening is that basically once you have this kind of bound, then you can interpret this as a bound on the vector. So you define the vector u of x, which is u1 of x up to u capital J of x, okay? Which is in Rj. And you view this as a random vector in Rj because x is also randomly distributed, okay, according to P note. And what's happening is that basically the L2 norm of U is almost surely bounded by C root J. Okay. Turns out that since you have this bound that's almost sure, you can actually apply known results in concentration of random matrices that allow you to basically show that the matrix 1 over n times the sum over I of u of xi, u of xi transposed, which is a matrix of empirical inner products of the basis functions uj's. This converges quite well to its population counterpart. And since the P note is upper and lower bounded and the uj's are orthonormal, then basically this is almost like an identity matrix in a way. And why is that useful? It's because when you look at the quadratic form defined by this random positive semi-definite matrix, actually it's exactly the quadratic form describing the empirical L2 norm. So what you're going to do, what does it allow you to do is basically you're showing, if you apply a matrix concentration result to this matrix here, actually you can show that you can relate with high probability the L2 norm and the empirical L2 norm just based on this kind of assumption on the basis. But the crux part of the problem of the proof, kind of, is that you can't consider arbitrarily high by a number of basis functions for this to work. You have to stop at some threshold capital J that's a little o of n over log n. So it's not a massive problem, to be honest, because actually in the proofs of non-parametric estimation, let it be like frequentist or Bayesian, you never need basis functions more than n basis function or n over log n basis functions. But there are some priors that are defined by infinite series, and for this I can't really handle them in all generality. Depends on how well the tail, how the tail is as posteriori. If the tail is small as posteriori, I can neglect the end of the spectrum in a way and focus on the first capital J of the eigenfunctions, and then I can apply the machinery here, basically. Okay, so basically, to sum up what we were doing, the way I'm suggesting to solve this kind of problem of testing condition for non-parametric regression is just to, as long as you have, you're in this kind of setting where your prior is defined by basis decompositions, and you have those assumptions here that are satisfied. So first one is to have an empirical L2 norm contraction rate. Okay, so that's something that's already provided to you by the theory that already exists because the empirical L2 norm satisfies the testing assumption. That you can approximate well F naught by elements of the span of the capital J first eigenfunctions, okay, or chosen capital J that's little o of n over log n. And also, more importantly, that the same holds for the posterior distribution on F, basically. So what that means is that you're looking at the distance as measured in the infinity norm to the span of the first J eigenfunctions of your output F, okay? And you want to ensure that basically the posterior distribution, the posterior probability that this distance is larger than the epsilon n, which is your rate in the empirical L2 norm, goes to 0. Okay. Then, in that case, basically, I can neglect what happens for the tail of the spectrum for this decomposition. I can apply my concentration equality, and then I get directly for free an L2 contraction rate instead of an empirical L2 one. And what's interesting is that basically, compared to the other approaches, we are just eliminating this kind of constraints on F0, which is like typically that before, instead of having a contraction rate in L2 that was valid for all regularity beta, we had a contraction rate in A2 that was valid only for betas larger than d over 2, and here we're basically going lower to this threshold. Almost for free, because basically all the assumptions that you need to satisfy, verify for this theorem to hold, you typically already use them in order to prove an empirical L2 norm contraction rate anyway. Okay, so I have a bunch of examples I could go through, but it's going to be too long. But yeah, you're very welcome to ask some questions if you want. Thank you.
Thank you very much, Paul. It's time for questions now. Next question.
Can you work with sieve priors?
Sieve priors?
Yeah.
I've never really worked with those, to be honest. I'm not really sure what it means exactly.
It will be a random truncation of a...
Oh, yeah. Yeah, of course. Actually, I can do more than truncation, actually. So here, for instance, you have a wavelet series that's truncated either deterministically or with a random truncation. And since for the priors that you take on the truncation, you always have that a posteriori the truncation will be less than some deterministic value that's always little o of n over log n. It's typically a power of n that's strictly less than 1 anyway. So the theory applies and yeah, it works. Otherwise, you also have like a soft truncation where you have like an infinite series, but you have exponentially decaying coefficients of this kind, so exponential minus t times a coefficient times the random function. And you put a prior on t, which just defines how much you're soft truncating the sum in a way. And the same thing applies, like a posteriori, the t is not too small, which means that you're truncating enough functions.
Any other questions? I have a short one. Okay, in the beginning you described for you use a nonparametric setting when you use testing conditions in order to get contraction rate. Do you know in the literature if there is a way not to use testing conditions, not testing condition values how to use idea about it?
Well, I don't really know over generic approaches, to be honest. It's more like a case-by-case kind of thing. So, I mean, if your model is conjugate and you're working in like conjugate GP and you're like basically, yeah, if you have like a Gaussian likelihood and a Gaussian process prior, then you have a Gaussian process posterior. But it's not really easy necessarily to see, even by the naked eye, if you know what the posterior kernel is, what the behavior is going to be. So yeah, I don't know. Otherwise, you have like you have other instances of conjugate situations where you could do an ad hoc proof instead of testing assumption, testing condition. But yeah, it's not that clear.
Are there any other questions?
Quick question, but the assumption on the right side, did you assume that they were RLP?
Yeah. In order to talk about L2 of P naught, P naught is the distribution of the X. Yeah.
Any other questions? Okay, let's thank Paul again.